Last minute revision part 3. I wasn't expecting this to drag on quite so long, I'm sorry. But if you've stuck with this and gone with it, hopefully it'll help you and we can get most of the paper for tomorrow kind of sorted for you. And if it's not, doesn't work out to be that way, then sorry, I'll just run away. So yeah, we've covered quite a few different topics in part 1 and part 2. We left off with nth term, I'm pretty sure. With this, looking at the difference between ones that go up that are linear, that go up or down by the same amount each time, and how you kind of find the number on the end by going back a number, and then comparing that with ones that go up by a different amount each time. Normally, actually 3, 5, 7, 9, that's the common one, and you have to write down then what n squared would be as a sequence and compare it with what you've got. Yeah, okay, anyway, the last few topics. Pretty confident on this one, maybe. 80 to 90% confident. Similar shapes. Nice, easy one to get you going here. We know this length and this length, so we've divided this by this to get the scale factor. And because I want because this is smaller than that, to go this way, I'm dividing by my scale factor. So that divided by 1.4 is 3.2. So scale factor by dividing big by small, and then if you finding something on the bigger one, times your scale factor, or if you're finding a side on the littler one, divide by your scale factor. The second one then said, okay, the area of the smaller shape is 10.4. What's the area of the bigger shape? Now, I think a lot of people might then just times by 1.4. They think, well, the scale factor is 1.4, I times it by 1.4. But it's the length that you times by 1.4. So if the scale factor is 1.4, the area scale factor is 1.4 squared, and the volume scale factor is 1.4 cubed. Okay, so in this case, it's the areas that we're working with. So I've worked out 1.4 squared. And because I know the smaller area, I'm timesing by my area scale factor. Alright, so area times area scale factor to get that. Just out of interest, what if it looks fairly similar, this, alright, clearly mine are just similar blobs, we'll call them. But I know the areas, right, and I'm missing a side. So by doing 160 divided by 10, big divided by small, which is 16, what I've actually worked out is the area scale factor to be 16. Right, not the scale factor. So I have to actually go backwards. So rather than squaring that to get that, I'm square rooting that to get that. Okay, so the square root of 16 is 4. So the areas, this is 16 times bigger than this in terms of area, but actually each side is only 4 times as big. So if this is 28, this one here is 28, and because it's smaller, I'm dividing by 4. The other way around, it'd be timesing. So 7 centimeters. So just be careful. If you're given areas or volumes, to work out area or volume scale factors, you'll have to square root or cube root, depending which, to get your scale factor. Quite common, okay? Trapezium rule we talked about in part 1. I did a question in this booklet on a cone with a cylinder. However, again, I did say this at the start of part 1, because there was a question on a sphere in paper 1, I don't know, I wouldn't get too stressed about it. However, if you do get something like this, it's asking for the surface area. Let's just look at the cone, right? For the surface area cone, if you look at the formula sheet, it tells you that the surface area of a cone is pi r L. Now, pi we know is 3.14. Okay, the radius is the radius of the cone, just like a radius of, right, which in this case was 5 times 5. But it does tell you, if you look at the picture at the front, that L actually is that length rather than the height, which is a straight height. Now, I was told that the vertical height is 10, but I don't actually know that. But there's a little bit of 3D Pythagoras, and now I haven't put 3D Pythagoras in here, but there is a small chance that your Pythagoras question tomorrow could be 3D Pythag. Not like this, so I wouldn't think, okay? But to work out that there, you can see you've got a right angle triangle within that cone, so I'd be doing square, square, add square root to get that. Then I can just dump that there and work out the surface area of the cone. But if you did get 3D Pythag, it's a lot more normal to see it in a cuboid, where, a terrible drawing, apologies, where you kind of, you're looking for right angles within the cuboid, okay? And now we're not going to talk about this here, but if you want to do anything on that and you're struggling with 3D Pythag, have a look at the booklet it's in, which I think is booklet D part 1, but come and see me and we'll go through one just before the exam if you want, okay? Next up, I've made a hell of a mess on this page, right? But what I just want to show you this. We're looking at arcs and sectors. A sector is a pizza slice, okay, basically, and an arc is the part is just kind of the crust of the pizza slice, if you were, right? So a sector is part of the area of the whole circle, whereas an arc is a small bit of the circumference of the circle. Now, the area of a circle is pi r squared, okay, and the circumference of a circle is pi times the diameter. If I wanted the area of this sector, I would do pi r squared times the fraction 50 over 360. If I wanted the area of this sector, I would do pi r squared times 310 out of 360. Okay, so knowing that allows me to work out that that's 310. If we then forget area and we look at the circumference, if I want the length of that arc there, it's pi times the diameter times 50 out of 360. But if I want the major arc, it's called, the big arc as opposed to the minor arc, the small arc, the major arc would be pi times the diameter times 310 out of 360. So that's all those four showing you. Area of the smaller sector, bigger sector, arc for the smaller sector, arc for the bigger sector. Then just pick out what they want. The first one here said, what's the area of the remaining shape if this was cut away? So I'm looking at the area of this major sector here. So this one, which is what I brought in that, into a calculator. Away you go. Okay. And the bottom one here said, what is the perimeter of the sector that's been moved? So I need to know how long, we're looking at perimeter, so I need to know how long that is. So I'm using that, which I've brought in there. Just be careful. All that will be, all I've worked out there, is the length of the arc. If they want the full perimeter, I'm also going to have to add on these sides, which in this example were 12 each. The radius was 12. So my answer down here, I would have to add 24. Okay, I'm just going to stay there a sec, actually, if hopefully I don't run out of time. How can I link, because this would come at the back of the paper, but they sometimes like to link it to, I've got a better drawing than this, here it is. They sometimes like to link these questions to sine and cosine rule. So if I was asked for the area of all that shape, I would be doing pi r squared, or pi, let's just do it properly, pi times 10 squared, times, that would be the full circle, but the fraction I want is 70 out of 360. So the area of that is that. However, if I then draw a straight line there, and I want the area of just that bit there, I'm going to need to find also the area of this triangle and take the triangle away from that to leave me with just the shaded bit. So this is currently the whole thing. If I can get the triangle, take it away, like I said, I'm left with just that. So how would I work out the area of that triangle? Well, this is how I can bring in that sine, cosine area, that kind of question, because we know that the area of a triangle when we're at the back of this is half AB sine C, right? So half times 10, but that is also 10. So you've got that triplet I talked about in part 1 of this video. So half times 10 times 10 times sine 70. So that is the area of the full thing. That would be the area of that triangle. Half times that times that times sine that. Take that away from there and I'd get that. So that's how I could kind of link that together. Sorry if that wasn't quite fully in view. Right. Back at the end, are we? Pretty much. Okay. Just some graphs and some trigonometry graphs in particular, right? Again, don't worry about this. It says tan 30 is equal to cos 150 is equal to, I think we got this one wrong. That was meant to, because, just put them in your calculator. Tan 30 equals, and your calculator tends to give you the third and fraction answer, and you'll find it's that. And cos 150, if you put in your calculator, I can't remember what it was. I don't know, I'm guessing. But just put in your calculator, you'll find the correct answer. Identifying graphs, you didn't have to do it in paper 1, but again, I'm not overly, right? I would just say be careful. That's a straight line graph, y equals mx plus c. That's a quadratic graph, it'll be something like y equals x squared plus something maybe. That's a cubic. If it bends twice, y equals x cubed. Then you've got these other two dodgy ones, which are this one, which is the graph of y equals 1 over x, just learn it off by heart, and this one, which is y equals, I can't even see that, y equals 2 to the power x or 3 to the power x or something. They call the exponential graph and the logarithm. Is that what it's called? Can't remember. Yeah, I think it is. But just be aware of it. Okay. In this case, I'm asked, what could this possibly be? Well, it's not a straight line. It doesn't bend once. It's one of these. It's a cubic. It's bending twice, but it's cutting through. It's going to have a positive y-intercept as well. So I'm looking for an x cubed with a positive y-intercept. So that one. All right. None of the others. That's an x squared. That's that would look like that. That's a straight line. That's a logarithm one because it's got a 1 over x, so it would look like that. And the last one is another x squared, so alright, so I hope that's okay. Right, the last topic then, trigonometry graphs. I'm going to do this in a bit of paper. You might be asked to sketch them. Okay, if you were I'm going to go all the way from minus 180 up to 360. You might only have to do a chunk. It could be minus 180 to 180. It could be 0 to 360. It's normally either that chunk or that chunk you're drawing, but I'm going to do the full lot. The way you would do it, it goes between, you'd need to put minus 1 and 1 on, remember to do that. They'll all run from minus 1 to 1. You need to put those values there along x. And let's start with y equals sine x. Basically, people, put all these numbers in. Instead of x, do sine of 0, sine of 90, sine of 180, sine, and blah, blah, blah. And what you'll find is, this thing actually goes, the sine of 0 is 0, the sine of 90 is 1, the sine of 180 is 0, the sine of 270 is minus 1, and so on. And actually this is down there and then there if you put them in. And what it does is you've got to make sure as well that you curve. Now it doesn't have to be any better than what I'm doing really. So it kind of curves like that. If you're drawing y equals cos x, it's the same thing, but when you put cos 0 in, it won't give you the answer 0, it'll give you the answer 1. So the only difference here is that this starts at 1. So it's quite nasty if you're drawing, if you have to draw that, because it almost looks like you're drawing a triangle, but you're not. You're going to have to remember that no, that curves in, that curves round underneath and back round, and then the same this way. So they're very, very similar, it's just where they start, okay? Tan x is a different beast altogether, y equals tan x. If you put the tan 0 in, it'll give you the answer 0. If you put that one in, it'll say error. If you put that one in, it'll say 0, and this one will say error, and this one will say 0, okay? And then this way again, this will say error, and this will say 0. The ones that are errors, you need to imagine a line being there, okay? The ones that are zeros, which are like in between the two lines, okay? You come from there and bend in, and then bend away. Bend in to the 0, bend away. There, I'm only doing I'm only doing the bend away bit because that's not needed. Okay, so where it goes through 0, bend into the 0, bend away, but the error lines, where it says error for these three, just make sure you draw a line down and never actually get to those lines. Almost touch them, but don't quite get there, okay? Right, but if they want you to do a calculation with it, something like this one, so here it's been drawn for me, and instead they're saying, can you solve cos x equals 0.342? Well, I don't need no graph to do that, okay? All I got to do to solve that is take the cos over. X equals cos minus 1, 0.342. I better actually do this in a calculator, and I get the answer. And if I put that in my calculator, I get the answer 70 degrees. Okay, that's good enough for a mark. So even if you ignore the graph and you just take the cos over, if it was sine, you take the sine over, if it was tan, blah, 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 you do the same. However, why give me the graph if I don't need it? Because if I know that the answer to cos x is 0.342, I just need to find my answer up here, which is about there. Ish. Right? Doesn't have to be perfect. If you draw a line across there, you'll find that it cuts the curve twice. Once there, and once there. Now, I already know that one of my answers is going to be 70. So that 70 must be that one there, because this would be 90. I'm surprised I didn't put that on. But I now have to work out what that is. Well, if that gap from there to there is 70, I assume I've got the same gap there. So this one is a 360 take away 70, which is 290. So my two answers here, 70 and 290. Now, be a little bit careful. The algebra will definitely give you one of the answers, but it might give you an answer that you don't need. For example, what we can't see here is that this graph continues in both directions, including this one. So there is an answer that is down here, right? Now, it hasn't happened here, but you might, particularly with the sine graph more than the cos, you might find that the calculator actually tells you that the answer to this is minus 70. And you'd have to spot, hang on, what the calculator has done is it's given me the answer that would have been further down than what I need. But it'll still help you work out these two, because if that's minus 70, that one must be plus 70, and then that one is 70 back from that, and so on, okay? So don't be put off if it gives you a negative answer to this, to the algebra bit. Just picture the graph continuing, but come then to the right hand side to work out your answers. The only other one that I thought was interesting here was, and rare, but sketch the graph y equals sine x plus 3. Well, we've already drawn sine x, there it is. But if you want to draw sine x plus 3, basically everything gets moved up 3. So the 0 moves up to 3, and the 1 moves up to 4, and the 0 moves up to 3, and the minus 1 moves up to 2. So I wouldn't need minus 1 and 1. What I'd be interested in is I need 1, and I've got to get, in fact, I've got to get up to 4. So whereas sine x would start there and would go to 1 and then would come below and whatever, if I move that up, that moves up 3 to there, that moves up 3 to there, that moves up 3 to there, that moves up 3 to minus 2, and so on, and basically it's just... Okay, also you will need to be put in there though 90, 180, 270 and 360 to show where those points are. You don't need to draw those lines up, obviously, but... Okay, so everything's just moved up 3. And finally, there were no transformations in paper 1. So just in case, if I am rotating, I will need trace in paper. I will trace the shape. I will also trace the center of rotation, in which case it says the origin, which is there, but it doesn't have to be. I trace the shape, I trace that. I put my pen on the center, not on the shape. I put my pen on the center and I turn it. In this case, I'm turning clockwise as opposed to anti-clockwise, so it's coming down here, and it would look like that. Use your tracing paper, see where it goes, okay? If it was 180 degrees, it would be down there, or anti-clockwise would be over there, but this one was clockwise. And lastly, I think, yes, lastly, some enlargements. Okay, I'm going to start by ignoring the question. I'm going to enlarge this. I'm going to use this as the center, origin, because it says use the origin again, but it doesn't have to be. And I'm going to enlarge by scale factor 2. Twice as big, twice as far away. That's what scale factor 2 means. Twice as big, twice as far away. Scale factor half, half as big, half as far away. Right? So how do I do that? Well, to get from there to there is 1 across and 1 up. If I need to go twice as far away, I'll go 2 across and 2 up. To get from there to there is 3 across and 1 up. If I want to go twice as far away, I'll go 6 across and 2 up. And you'll find that the shape becomes 1, 2, 3, 4, 5, 6, becomes twice as big and twice as far away. Okay? But what it's asked for is minus 2. In this case, the minus means in the opposite direction. So rather than me double, instead of going, I said 1 right, 1 up becomes 2 right, 2 up. Well, if it's minus 2, right and up becomes left and down. So instead of 2 right, 2 up, I'm doubling it in the opposite direction. So 2 left and 2 down. 3, 1 in this direction becomes 6, 2 in the opposite direction. And you actually find that you get the shape that is double the size, but in the opposite direction. Now, in my final 30 seconds, ignore what I drew there. What if the two shapes were drawn and they said describe the transformation? You'd be going, okay, first of all, this is bigger than this. It looks like a rotation, but it's not, because this is bigger than this, so this is an enlargement. Okay, then draw rays, connect the corners. So I'm connecting this corner to this corner, and this corner down to this corner, and so on, and this corner up to this corner, and you get it. And you'll see that all these lines go through the same point. That is your center of enlargement, okay? So center of enlargement where all these lines cross, and in this case it's 0, 0, or the origin. And then look at, okay, I'm going from there through there down to here, but how much bigger in this is twice as big? So the scale factor is 2, but it's not twice as big in the same direction, it's twice as big in the opposite direction, so the scale factor is -2. So that's how you'd work backwards to kind of get the question given the answer. Good luck, all the best. Come and let me know how you get on. These videos will go tomorrow, other than the booklet ones that I'll leave on, but these 3 that I've done today, I don't think are used to anyone by you guys. So all the best, and let us know how you got on. Bye bye.